Welcome back to Cosmos in a Pod.
Yeah.
Today we're diving deep, really deep into something pretty wild.
Oh, yeah.
Neutron stars.
Okay.
Ever thought about what happens when a star way bigger than our sun just runs out of fuel and kind of implodes? It's pretty intense. We're talking about a star so massive, many times the mass of our sun, and it collapses in on itself with so much force that, get this, it squeezes protons and electrons together.
Whoa.
Yeah, and they form this incredibly dense ball, almost pure neutrons.
So all that stuff that makes up a giant star gets crammed into a tiny space. How tiny are we talking here?
Think of a city, like maybe the size of New York or London.
Wow, okay.
Yeah, that's how small a neutron star can be. But here's the kicker.
Yeah.
This city-sized thing can weigh as much as our whole sun.
Hold on. So a whole sun squeezed into Manhattan. My brain's already hurting. But wouldn't something that massive, compressed that much, just keep collapsing? Into, I don't know, nothing. That's where things get really interesting. See, the collapse is dramatic, sure, but there's this force fighting back against gravity.
Oh, really? What's that?
It's called neutron degeneracy pressure.
Okay.
It's this quantum mechanical effect. And it basically stops neutrons from being squeezed too close together.
So it's this cosmic push and pull. Gravity's trying to crush everything, but then this neutron pressure is pushing back.
Exactly. That battle, that's what creates a neutron star. It's like the universe is saying, okay, gravity, you can squeeze, but only so far.
So a teaspoon of this neutron star stuff, would that weigh billions of tons, heavier than Mount Everest?
More like a billion Mount Everest crammed into a teaspoon.
Jeez.
It's almost impossible to wrap your head around it, the density. And that density, that's what leads to some pretty crazy physics.
Okay, back up a sec. You said these things, neutron stars, they're born when these massive stars die.
Right.
What actually happens during that? Walk me through a star's demise.
All right. So picture a star much bigger than ours, right? It's starting to run low on fuel. The nuclear reactions that powered it, they start to fizzle out. And without that outward pressure, gravity takes over.
So it's like letting the air out of a giant balloon. Everything collapses inward.
More like detonating a cosmic bomb. The core implodes, sends out the shock wave, blasts the outer layers of the star into space, and that's a supernova.
Wow.
Yeah, it's one of the most energetic events in the universe, visible across huge distances.
That sounds dramatic. So that's like the star's grand finale, right? The supernova, scattering its remains everywhere.
In a way, yeah. But amidst all that chaos, the star's core, it survives.
Really?
Yeah, crushed down to unbelievable densities by that supernova force. And that's what's left, a neutron star.
So it's like a phoenix, but instead of fire, it's born from this collapsing star.
That's actually a pretty good analogy. It captures the essence. This dense core, now a neutron star, it's left spinning super fast, like a memory of the star it used to be.
Okay, started to get it. We have a big star, it runs out of fuel, core collapses, boom, supernova. And from that explosion, this tiny, super dense neutron star. But you said it's not just a simple ball of neutrons, there's layers, right?
You got it. Not just a giant ball of neutrons. Neutron stars are, well, they're kind of like cosmic onions.
Uh-huh, okay.
Layers, each one weirder than the last.
I'm intrigued. Peel back the layers for me. What are we looking at here?
Okay, imagine you could slice a neutron star in half. Right on the surface, there's this outer crust, incredibly dense, but still made of atomic nuclei and electrons, like a super strong, super dense version of the Earth's crust.
So like a shell of superatoms. And under that?
Deeper down, things get stranger. Inner crust, it's this bizarre mix. Free neutrons, nuclei, electrons all jammed together. Doesn't exist on Earth, this state of matter. Then there's the outer core.
Okay, getting weirder by the layer. What's going on in the outer core? More neutrons.
It's thought to be this swirling sea of neutrons, protons, and electrons, but not just any sea. It's a superfluid, flows without any friction.
Hold on, superfluid. Like if I poured a glass of this stuff, it'd flow right through the glass.
More like it would flow through anything. Walls, containers, you name it. It's like gravity doesn't even work on this stuff.
Mind officially blown. We're not done though, right? There's still the inner core. What's at the heart of a neutron star?
The inner core. That's the real mystery. We can't see it directly, so we gotta rely on models and theories.
So what are the theories? What could be down there?
Some scientists think it might be something called quark-gluon plasma. It's where the building blocks of protons and neutrons, they break apart. This stuff might have existed just moments after the Big Bang.
So matter from the beginning of the universe.
It's possible.
That's incredible. And if it's not that, what else could it be?
Some think it could be something even more exotic, something we haven't even thought of yet. Matter so dense, so strange, it breaks the laws of physics as we know them.
So neutron stars, they're not just leftovers from dead stars, they're like windows into the biggest mysteries of the universe.
They are natural laboratories for extreme physics, pushing the limits of what we know about matter, gravity, and reality itself.
Wow. I think we need a minute to process all that. We're just getting started, though. Stay tuned for part 2. We'll uncover even more about these crazy objects.
Back again for part 2 of our neutron star deep dive.
Last time we were talking about, well, the possibility of a neutron star's core having matter from the very beginning of the universe.
Yeah, it's a wild thought, isn't it? And that's just one reason why these things are so fascinating. They're not just dense, inert objects. They're dynamic, energetic, and they influence everything around them in crazy ways.
You mentioned something about insanely strong magnetic fields last time. I'm picturing like a giant space magnet, but I have a feeling that's not even close.
Oh, understatement of the century. We're talking magnetic fields billions, even trillions of times stronger than Earth's.
No way. Okay, how powerful are we talking, really?
Imagine a magnet so strong, it could rip the iron from your blood from thousands of miles away.
Whoa, that's intense.
Yeah, that's the kind of power we're dealing with. These fields can warp space-time, distort atoms, unleash huge bursts of energy.
That is terrifyingly awesome.
Yeah.
What even creates magnetic fields that strong? Is it just the density?
It's a bit more complicated than that. Remember how the core of a massive star collapses during a supernova?
Yeah.
Well, as it shrinks, the magnetic field lines, they get squeezed together, amplified like crazy. Like compressing a spring, the tighter you squeeze, the more energy you store.
So the star's death throes, they fuel this insane magnetic field.
You could say that. It's the death of the star that births a neutron star with a magnetic field unlike anything else out there. And that magnetism, that's what leads to some pretty crazy stuff.
Like what? I'm all ears.
Well, it's responsible for those cosmic lighthouses we call pulsars. Remember we talked about how neutron stars spin really fast?
Yeah, stars spinning hundreds of times a second. Hard to forget that.
As it spins, the magnetic field channels these beams of radiation out from the poles. They sweep across space, like a lighthouse beam. And if Earth happens to be in the path, we see these pulses. Radio waves, X-rays, even gamma rays.
So the pulsing, it's not the star turning on and off. It's just the beams sweeping past us like a cosmic strobe light.
Exactly. And the faster the spin, the faster the pulses. We've even found pulsars spinning over 700 times a second.
700 times a second,
Yeah.
sending out pulses like a cosmic machine gun?
You got it.
Are all neutron stars pulsars, though?
Not necessarily. Some, their beams might not point towards us, so we never see the pulses, and some have weaker fields, so they don't make those strong, focused beams.
So there could be a ton of them out there we haven't even found yet.
Absolutely. We've only just started to discover these things. There could be billions in our galaxy alone.
Wow. You also mentioned something called X-ray binaries. Remind me what those are.
Sure. Remember the crazy strong gravity of neutron stars?
Yeah, the iron ripping from your blood kind of gravity.
Right. So imagine a neutron star orbiting another star. That gravity, it pulls material off the other star, creates a swirling disk of gas around the neutron star.
Like a cosmic vampire sucking the life out of its neighbor.
Dramatic, but yeah, kinda. As this material spirals in, it heats up to millions of degrees, and it emits intense X-rays. That's an X-ray binary. They're some of the brightest X-ray sources we can see.
So the neutron star, it's using its gravity to power this X-ray cannon.
That's a good way to put it. We can detect these blasts across the galaxy.
It's crazy how these dense little things can have such huge effects. They spin, they pulse, they shoot out X-rays. What can't they do?
And that's not even all. They also help us understand some of the biggest questions in physics.
Okay, tell me more. I love this stuff.
Their extreme density, it lets us study how matter acts under conditions we could never create here, like a natural lab for nuclear physics and quantum mechanics.
So they're helping us figure out the nature of matter itself.
Exactly. A window into the fundamental building blocks of everything. And because of their strong gravity, they're also perfect for testing Einstein's theory of relativity.
You mentioned gravitational waves earlier. How do those fit in?
Gravitational waves, they're ripples in space-time caused by, well, massive objects accelerating. And when two neutron stars collide,
What happens?
they create some of the most powerful gravitational waves in the universe.
We can detect that here.
Yes. We have these super sensitive instruments called gravitational wave detectors. They measure tiny distortions in space-time. And in 2017, we detected waves from a neutron star merger for the first time. Huge moment for science.
I remember that. Big news. What did we learn from that?
Well, it confirmed Einstein's theory even further. It showed us how heavy elements, like gold and platinum, are made, and it helped us measure the expansion of the universe more accurately.
So the gold in my ring, it was probably made when two stars crashed billions of years ago.
It's pretty mind-blowing, right? The elements that make up everything, us, our planet, everything we see, they came from stars and these neutron star collisions.
It makes you feel connected to it all in a way.
Yeah, we're all stardust. And studying neutron stars helps us understand that connection, how we fit into this big cosmic story.
That's awesome. Do you have any favorite examples of neutron stars or like exciting discoveries?
So many. But the Crab Pulsar is definitely up there.
The Crab Pulsar, what's special about that one?
It's beautiful, for one thing. It's in the Crab Nebula, which is this incredible supernova remnant. Chinese astronomers saw the explosion back in 1054 AD.
We've known about this thing for 1,000 years.
Pretty cool, right? And the pulsar itself, it spins about 30 times per second. We can see its pulses across the entire electromagnetic spectrum, radio waves to gamma rays.
Like a cosmic disco ball.
Yeah. Studying it has taught us a lot about how pulsars work, their magnetic fields, how they interact with their surroundings.
It's amazing how we can see these things so far away and learn so much. Shows you the power of science and how curious we are as humans.
Absolutely. Speaking of discoveries, what about the fastest known pulsar?
Okay, now I'm really interested. How fast?
This one's spinning over 700 times per second.
700. That's insane. I can't even imagine.
It really pushes the limits of what we thought was possible. Helps us refine our models of neutron stars, how they're structured, how stable they are.
Every discovery opens up new questions, challenges what we know, but there are still so many mysteries about neutron stars. What are scientists still trying to figure out?
One of the biggest is what the inner core is made of. We know it's dense, but not the exact kind of matter.
You mentioned quark-gluon plasma before.
Yeah, that's a possibility. Quarks and gluons, the stuff that makes up protons and neutrons, are no longer bound together. It probably existed right after the Big Bang, and maybe it exists in the cores of neutron stars.
So we could be looking back at the beginning of time by studying these things.
Exactly. Another question is what causes those massive bursts of energy we see from magnetars?
The ones that outshine entire galaxies for a moment.
Yeah. We think it's got to do with their super strong magnetic fields, but we don't know the exact mechanism.
Sounds like neutron stars are full of surprises. Any other mysteries that you think are really interesting?
One that's always fascinated me is how a neutron star tips over and becomes a black hole. What's the mass limit? What happens at that point?
It's like a cosmic cliffhanger.
Right. These are just a few of the mysteries that keep us astrophysicists up at night. They're like cosmic puzzles, each piece bringing us closer to understanding the big picture.
It's been amazing, this journey into the world of neutron stars. We've learned about their formation, how they're built, their crazy properties, how they help us understand the universe, and it sounds like we're just getting started. Welcome back. Final part of our neutron star deep dive. It's been a wild ride exploring these objects that just break the laws of physics as we know them.
It has been quite a journey, from their violent beginnings to, well, everything we talked about. The timekeeping, the gravitational waves, it's all a glimpse into the most extreme places in the universe.
Yeah, and like we said, they're not just fascinating on their own, they're tools helping us figure out the secrets of, matter, gravity, how the whole universe evolved.
Exactly. They're cosmic laboratories letting us study physics under conditions we could never dream of replicating here.
So before we finish up, what are your final thoughts on these things? Neutron stars. Why should we, down here on Earth, care about these distant, crazy objects?
It's a good question, and I think the answer is all about how connected the universe is. Neutron stars might seem remote and alien, but they're tied to our very existence.
Really? How? How do they relate to us down here?
Remember how we talked about neutron star mergers creating those heavy elements? Gold, platinum.
Yeah, still can't get over that. My jewelry, forged from stars colliding billions of years ago.
It's not just jewelry, though. Those elements, they're scattered everywhere. They become part of planets, stars, even life.
So we're made of stardust, and a good chunk of that stardust came from neutron star collisions.
That's the idea. The calcium in your bones, the iron in your blood, all created in stars and those fiery neutron star mergers.
Wow, that's humbling in a way.
It is. We're connected to these events, carrying the remnants of stars that lived and died long ago.
And by studying them, We're not just learning about them, but about ourselves, our origins, our place in the universe.
Exactly. It reminds us that we're part of something so much bigger, a cosmic story that unfolds over billions of years across these huge distances.
Yeah, and a story that's still being written. With every new observation, every new technology, we're understanding neutron stars better, their role in how the universe changes and evolves.
And there's so much more to learn. We barely scratched the surface. What are their cores really made of? What causes those magnetar bursts? What's the tipping point between a neutron star and a black hole? We're still figuring it out.
It's exciting to think about what we might discover next.
That's the beauty of science, a constant journey, exploring and discovering. And neutron stars, they're some of the most intriguing guides we have.
I think we've covered a lot in this deep dive. How they form, their structure, those mind-blowing properties, the different types, how they help us as tools. So much to explore.
And hopefully we've inspired our listeners to, look up at the night sky with a sense of wonder and appreciation for these incredible objects out there, spinning, pulsing, making us question everything we thought we knew.
Definitely. It's been a fantastic journey. Thanks for being our guide through the world of neutron stars.
My pleasure. And remember, the universe is full of wonders. Keep exploring, keep asking questions, never stop learning.
Couldn't have said it better myself. Follow and subscribe to Cosmos in a Pod for more fascinating insights into space and science.